Well, Chapter 12, Liquids, Solids, and Intermolecular Forces. So we were talking about, we had been talking about gases before we jumped ahead to Chapter 15. And one of the postulates of the kinetic molecular theory for gas is that there's no interaction between gas molecules. There are interactions between molecules, and the reason that we have solids and liquids is that there are interactions. And so we're going to learn about what those interactions are. Have you ever wondered why things taste the way they do? How do we taste things? What makes some things taste sweet and some taste salty? And what is that all about? Yeah, but how does a sugar molecule interact with your tongue and tell your brain that's sweet? Well, it touches it, yes. So it has to do with interactions between the molecules in your tongue and the molecules of the food that you eat. We have specialized receptor cells on your tongue, and they only recognize certain types of molecules. And so here's the illustration of a man drinking coffee, which, I know some of you had this morning. So coffee has kind of a bitter taste to it, which is a taste that I personally detest. I've tried to like coffee. I am of Swedish descent. I should be liking coffee. I blame it on my grandfather. Swedish grandfathers are supposed to bounce their babies on their knee and feed them spoonfuls of coffee, and my grandpa didn't do that. So it's his fault. I don't like coffee. But why does coffee have that bitter taste? Well, it's because how the molecules in the coffee interact with those receptors on your tongue. And that interaction is governed by intermolecular forces. Intermolecular. Inter means between molecules. Okay, there's intramolecular, within a molecule, and inter. Like intercollegiate sports are between two different colleges. Intramural sports are within the same college. So intermolecular forces that exist between molecules. Many physiological processes that occur in any living organism are dependent on these intermolecular forces. There are the more specific ones, such as how things taste, and there are also less specific ones that exist between all atoms and molecules. And these intermolecular forces of attraction are responsible for the very existence of liquids and solids. How does the liquid in that cup, the water, stay together as a liquid? Why don't the particles fly apart and become a gas? We know that water can be in the gas state. Why isn't it? Because there are attractive forces between the gas molecules. And so that's what we're studying in this chapter. The physical state, that means whether it's a gas, liquid, or solid, of matter is going to depend on how strong the intermolecular forces are, the forces of attraction, relative to the thermal energy. Thermal energy is related to the kinetic motion of the particles. And so the more kinetic energy that a particle has, that's going to oppose the intermolecular forces. Intermolecular forces are kind of, one book I used called it stick togetherness or stickiness. It's a little bit like Velcro. So if things are moving slowly, the Velcro is going to be stronger. It's going to hold them together. But you can tear two Velcroed things together. They're Velcroed together. My words are getting all jumbled up. Not enough caffeine, perhaps, because I don't like coffee. It's a problem. Velcro. So two Velcroed things, and they're stuck together. But if you rip it off, it will come apart. And so the motion is the things pulling away from each other, trying to move, and that opposes the intermolecular forces. Everything's moving, and the thermal energy is that motion. Question?
Is thermal energy and kinetic energy synonymous? Are they synonymous, or are they just similar?
That's a good question.
So thermal turn into kinetic.
I'm not willing to say on YouTube that thermal energy and kinetic energy are exactly the same. They are directly correlated in terms of particles. Because we use kinetic energy, you could talk about the kinetic energy of a car. Would that exactly be thermal energy because it's moving faster? Not necessarily. But when we're talking about on the particle level, yeah, I think they're the same. So talking about gas molecules or liquid molecules moving. So the warmer something is, the more thermal energy it has, the more movement the particles have. So if you have a substance that has very weak intermolecular forces, the particles are not very attracted to each other, then those are going to melt and boil at a lower temperature. They're more likely to be in the gas state at room temperature. So helium gas, helium is a gas at room temperature. I think its boiling point is down close to 0 Kelvin. It's really, really low because there's really almost no interaction. There's no attraction between the helium molecules, even when you get them close together. There's just nothing to hold them together. So they just fly apart. If you have something with very strong intermolecular forces compared to the thermal energy, then it's going to be a liquid or a solid at that temperature. As you warm it up, the thermal energy gets more important. The intermolecular forces do not depend on the temperature. So as you warm something up, it will start to melt and then to boil into the gas state.